Dear friends, welcome to this lecture 20. So we are at the end of this beautiful journey. So lecture 20. And this very last lecture is devoted to the study of, it is devoted at least not to the study, but to show you how to describe the behavior of a completely new tool to create artificial motion. And I will show you now some of these examples, but before I will tell you very quickly how do they work, and then I will try to describe it with the theory of nonlinear elasticity. So what I'm going to talk about today is these electroactive membranes. Now, essentially, how do they work? Well, essentially, you probably remember from if you did it in some of your courses, but if probably this is something which you normally have from my school, and knowledge that you already have from my school. So you certainly have seen what capacitors are. So capacitors are essentially made of a small insulating material, of an insulating film. I am exaggerating the thickness here, and in between this insulating material is put between two plates, and the two plates are two electrodes. And if you remember, this is really what in physics is called a capacitor. Yes, so normally what you do is you apply a voltage, and for example, on top there is plus charges and below these minus charges. Yes, so now for classical electronics, this is it remains like that, and it doesn't really deform. You clearly see that there is an attraction between plus and minus, but this attraction doesn't really deform the material, because this is very stiff in classical electronics. However, if instead of putting something hard inside of these two electrodes, you put something very soft, then what happens is that the so like for example a silicon sheet or some polymeric material insulating, then what happens is that the plus and minus, they compress the thickness direction, and since they compress this film in the thickness direction and this guy is incompressible, it has to expand in area. And since it expands in area, its deformed configuration, I will draw it just like this. So it means that after the deformation, after the application of a voltage, then that object, oops, I want to use the right color, that object would deform in this way. In other words, you see the area is increasing. And by the way, it can increase a lot. Of course, to secure that the electrodes do not break during this process, these electrodes are made of a very compliant material. So in other words, they're made of grease in some applications, sprayed grease. But what it is important here is really the idea that the thickness, the reduction of thickness, which is induced, is determined by the application of a voltage, leads to thickness reduction. So application of a voltage, thickness reduction, expansion in area. And what it is important is that if you take this distance here, so let me say this displacement from this point to this point, well, this displacement can be great. It can be up to 6-7 times the original side, so the original length of the membrane. So for this reason, these membranes are used for actuation, which means to create artificial muscles and to create, as you will see, flying objects and so on. And I will tell you a very funny story at the end of this, but also to harvest energy. but let me show you some video before. So these are, I want to start by this first example here. So look at this. So I will explain to you a little bit how do they work. Oh, something I want you to know is that there are many companies working on this, and I may have mentioned already that Facebook is actively working on soft solid. So look what you can happen. So you see, this is the membrane, is pre-tensioned by some pre-stretched frame, and when you apply the voltage, this happens. So you see, these type of things, there's nothing on Earth that no technology, no existing technology so far can do this. But with the application of a voltage, you can. So you see, this is, try to imagine what you can do. You could actually build some flying object, yes? So I'm just playing it over and over, but if you excite it periodically with a voltage, then you could do this. And of course, it's not the only application that you can do, but you can, for example, create loudspeakers. So you see this. And of course, I have to say that this is even an old video, but more recent videos more recent applications are already almost at the level of prototypes. Now, what is the problem of these devices? The problem is that if they deform, and this is the very last video that I'm about to show you here. Now you see, I don't know if you can interpret correctly this image, but I will get back on these later. You see, these are the electrodes. One goes above, the other one goes below. So it's just like this scheme here. You apply a voltage, you gradually increase the voltage. There are these little, what is the English name of these? These little forks at the extremities, they pinch this membrane, and at the extremities, I don't know if you can see, there are some weights hanging. So in other words, gravity goes in the perpendicular direction, downwards. So what happens is that, so there is a load applied radially to the membrane, and when you increase the voltage, this is what happens. It increases, it expands, and at a certain point, it breaks. So you see, so there are limitations, and of course, with all the things that you do in science, you want to understand how much you can stretch the thing that you want to design in order that it doesn't break. And in this lecture, I will try to explain you how these membranes work in the simplest possible way. So, since my target is simplicity, as you may have already guessed, the right choice is to go for an energetic approach. So I want to show you an energetic approach to the modeling of electroelastic membranes. Sometimes I have to say I've been using some different wording. Sometimes they're even called electroactive polymers. So if you want to look it up in internet, then they're named like sometimes abbreviated like EAPs. So first of all, I want to describe essentially what happens here, and I want to make a little scheme of a little membrane, and then I will have to explain how to formulate it energetically. Before formulating the problem energetically, I just remind you, just a very quick reminder, and this remark is already present in previous lectures. We've seen that for the simple case of a spring, I want to use this idea. This is the idea I will use in this lecture. So if I have a spring with an elastic constant K, and the spring is under the action of a force F, then to find the elongation of the spring, which I call X, then I simply have to compute the minimum of the elastic energy of the total potential energy U, which is equal to 1/2 of K x squared minus the work of the force F times the displacement x, okay? So this would take the name of energy, and in this case it would be an elastic energy, and this term here take the name of work. That we did already see, and if you think about it, these x would be the work. I mean, initially imagine that the force is located here when the spring is unstrained, and then the work is done by the magnitude of the force times the displacement. What I already did in one of the last lectures when I was talking of the energetic approach to the Poynting effect is simply that the equilibrium configuration you can be obtained by simply computing the stationary point of the energy. And if you do that, you actually obtain that this is equal kx minus f, from which you get that f is equal to kx, okay? This is the very idea I will be using in this approach, energetic approach to the modeling of these membranes. So first of all, let me start a description of the membrane. So first of all, I assume that in its I have a flat membrane. This is a flat membrane, and we could assume that it is a square, for example, and we can assume that it has edges given just equal edges, and we could assume that this membrane, this edge has a length L, and this has a length L. And also I will assume that the reference configuration, this reference configuration has a thickness H, okay? So this is my reference configuration. Okay. Now what happens is when this membrane is being deformed, I can assume, for example, that the membrane is deforming in equibiaxially. So what does it mean equibiaxially? So let me take equibiaxially means somehow intuitively. What does it mean? Well, it means that this membrane during its deformation, it stretches in this direction and in this direction exactly of the same amount. So let me draw in this second configuration the equibiaxially deformed membrane. It will be more flat. Sorry, it will be in any case flat like that. So the membrane is increasing its dimension, and as a result, the thickness is being reduced. Okay. So, well, I'm trying to represent the fact that the thickness is smaller. And this thickness in this current configuration is lowercase h. And let me say that this edge now will have a length lowercase l, okay? And also this one is lowercase l, okay? So essentially what I am doing here, I am describing, this would be the current configuration. And in particular, I will, once again, I want to stress, I am considering what is called equibiaxial deformation. Okay, so what does it mean equibiaxial? Well, it simply means that the membrane deforms exactly of the same amount in these two directions. Okay. So to describe the deformation, I will be very sketchy in this proof. It won't be a very detailed proof, but let me say that, for example, I decide that this is direction 1 and this is direction 2 and the perpendicular is direction 3. So let me say this is 1, 2 and 3. And also, of course, in this configuration, this is 1, this is 2, and this is 3. So first of all, I want to deduce the gradient of deformation. Well, in this case, I just want to study an homogeneous deformation. So if you see, I want to describe the deformation F that brings this guy into this guy, and I will already start it in terms of the gradient of deformation capital F. So how is this capital F done? Well, this capital F will, if I write it in this reference, it will be done as follows: lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3, right? I mean, this would be where in this case, clearly, lambda 1 will be equal to clearly lambda 2 because we're studying this equibiaxial deformation, and this is equal to what? Well, it will be equal to the length after deformation of the edge of this square divided by the unstretched length, and where the thickness lambda 3 is related to the change of thickness, and this is h divided by capital H. Also, I want to confine attention to situations where the membrane is incompressible, because this is in fact the most common case. Silicon is normally incompressible, so silicon or similar material used for these applications are in fact used for EAPs are essentially incompressible, and if they are incompressible, then clearly it must result that the determinant of F must be equal to 1. Now if I compute this is a lambda 1. Now lambda 1 is equal to lambda 2, so this is lambda 1, let me just put it, so lambda 1, lambda 2, lambda 3. So let me agree that from now on, since I will be interested in the study of the planar deformation of this membrane, this is just, I set lambda 1 and lambda 2 equal to lambda, okay? So, well, from this expression you get that the incompressibility condition gives you that lambda squared times lambda 3 must be equal to 1. So you see from this you get that lambda 3 must be equal to lambda to the power minus 2. Okay, with this in mind, we already know that the gradient of deformation, let me just maybe cancel this lambda from here. I will just write it on top. So let me just write that we set the common value of these equal to lambda. And for this reason, with this choice, we see thus the gradient of deformation takes the following form. It would be lambda 0, 0, 0, lambda 0, 0, 0, lambda minus 2, right? Another thing I want you to see, which is very important, let me draw the, let me ideally take this membrane and I put it on top here, center it. So I would just put it dashed, okay? So, well, that would be, roughly speaking, this. If you could see the shadow of that membrane in the current configuration, this would be this, yes? So you see that the edges essentially are displacing of a total amount which is given by L minus L, right? So essentially, well, we see that the displacement of the boundary, I want to mark it down because it will be important later on when I write the work. The displacement is essentially U, and let me say this would be U divided by 2 and U divided by 2, and this would be again U divided by 2 and U divided by 2, so that the total displacement is equal to U for, imagine, what I mean by displacement is how do they displace with respect to each other. Then this U is clearly equal to L minus capital L. So if you remember that L is equal to lambda, then this is equal to lambda L minus L, which means essentially L times lambda minus 1. Okay, so let's keep this in mind, and this will be important now. Okay, so what is the setting that I am studying, in which I am studying this problem? So what are the electromechanical conditions that I am applying to this device? Well, again, let me draw this device in its undeformed configuration. So imagine we have this guy, which is very thick in its reference configuration. And essentially what I do here, I imagine to apply loads that I draw in this configuration, and I imagine, because I assume to denote them as nominal stress, so nominal stress written in the reference configuration, as you should remember from the lectures with Michel. So imagine that at the same time you are applying forces at the edges. I'm not doing these by my fancy, but rather I want to show you again this picture. So I won't play the movie now, just a second. I'm just trying to reproduce what you see here. You see, so there is the membrane, there is the upper electrode, the lower electrode. I am supposed to apply voltage. So let me apply just, I write, just for clarity, I am applying one electrode here and one below, and I am attaching them to a battery. So I'm applying a voltage, so which is exactly what is happening here. So you see these two strings, and then of course, okay, this is circular, I'm taking it square, but it won't change anything. And I'm applying forces S to this membrane. Okay, so this is, imagine this force S. So in fact, this is not force but a stress S. Okay, so that's the idea, and what I want to do is for each instant try to understand how does this object deform. So there's a protagonist I haven't talked yet, and this protagonist clearly badly calls to be called in. And who's this guy? It's clearly the electric field. So when I put charges here, and imagine you put charges plus on top, and of course on the other side there will be charges minus on the other face, then you clearly see that there will be an electric field. And without entering too much into the details, we don't need to say too much, I just need to tell you how to compute. But the electric field in this membrane, in fact, it will be directed in this way. Okay, so these that I'm denoting here, these little red vectors that I'm denoting, these would represent the electric field. Now, this little vector that I've denoted here, actually, it has to be computed. So this is in fact a vector. It has the direction of the say unit vector in this direction. Not to avoid confusion, let me just say this is k. The magnitude of this guy is given by the ratio between the voltage, this V here is the applied voltage, and this is the voltage divided by the current thickness of the membrane, and it goes along k. Now in this present situation actually is going in the other way around, so let me just put a minus in front. Okay, so that what you see here, this is the electric field in the membrane, Okay, so now with this in mind, we have to understand how to model, and you don't worry because this is essentially almost over. Because this is, by the way, the beauty of the energetic approach. How do we describe the equilibrium configuration of this thing? Well, first of all, we have to write the say, energy of this object. So, but in this case, we will have to write not an elastic energy, but an electroelastic energy. Let me be more clear. So, let us assume that the specific electroelastic energy of the membrane, which means energy per volume unit, written in the reference configuration. Well, this energy, let me assume, it's given as follows. Look, I'm calling it W star, just to say that it's not completely, not the one that we have already seen. Let me say that this depends on the first invariant of the deformation. We know what it means. And it also depends on the electric field, okay? And this energy is actually written as follows. Look, it's written in the following simple way. There is a first part, W, which is the purely elastic energy. This is nothing but what we have already seen. And for example, we will assume that this is a new Hookean. But in any case, this is the purely elastic energy, okay? Well, there's no surprise in these expressions. So these part of the energy is simply accounting for the elastic deformation of the membrane. And then there is the electric part. And so I will add plus, let me say, psi. And this psi depends on this little electric field here, E. So say I'm assuming that the only change that is made to the energy of this device is enters the problem through the energy. So essentially, the total energy, the total say internal energy of this device is done of a sum of a purely elastic part and an electric energy density. Now, for the purpose of clarity and simplicity, I will take into consideration a special form of this psi, and here we will assume that this psi is written as follows, is 1 is equal to minus 1/2 epsilon, and this epsilon takes the name of dielectric permittivity, and then there is the magnitude of the electric field squared. That's it. So you see, there's no real major variations with respect to what we would do normally. If I compute this expression based on the value that I've given you for the electric field, so this electric field, you see, the important feature is that this electric field depends on the voltage, but it depends on the current thickness. So as the thickness is reduced, the electric field increases. So you see, I want you to understand a little bit of what is written here. So in fact, just let me be more clear. If I remember that H is equal to lambda 3 capital H, then this expression where the magnitude of E, well, this is just, well, it would be squared. It would be the vector above is V squared, which is the controlled voltage, divided by capital H squared. But due to compressibility, if you remember, H is equal to lambda 3 capital H, but this is nothing but lambda minus 2 capital H. You remember, this is due to the incompressibility. So for this reason, we see that in this application, the electric energy density, this is equal to minus 1/2 epsilon. I forgot to write here what epsilon is. So this epsilon takes the name of dielectric permittivity or dielectric constant. It's a material parameter that tells you how good this insulant is. This is 1/2 of this. And then inside here, I have to write, now look, instead of writing, so I should write this quantity here, but instead of writing this, I have to write, so you see, I have discovered that H is equal to this guy. And well, when I do that and I replace, I simply obtained that this is equal to capital B squared divided by H squared times lambda to the power 4. You agree? Because you see, these below here, there should be lambda to the power minus 4, but then I can bring it above. So essentially, we found that, for example, if the material behaves as a Newton, so if the silicon behaves as a Newton, well then the energy that we see there can be simply written as follows: W star equal to, well, there would be mu divided by 2, and then here we would have I1 minus 3, and then minus epsilon divided by 2, V squared divided by H squared times lambda to the power 4. That's it. So this is the energy in the membrane. So you see, there is only one difference with respect to the usual situations, is that there is a term which is due to the fact that in the membrane there is the presence of an electric field. So, well, with this in mind, how do we find the equilibrium configurations? Well, we simply have to write the work, the total, we simply have to write the total potential energy. So let me write it here. Total potential energy. What is this? Well, you remember, the total potential energy is given by the integral of the internal energy minus the work. Let's do it. So the total potential energy U, this will be equal to what? Well, first of all, don't forget, this is just the specific energy. So this is energy per unit volume. What is the volume of this object here? Well, the volume is equal to, so this is capital L, and this is capital H. So the volume is L squared times H, and then this multiplies my W star. Yes? And then I have to write minus the work of all the forces acting on the membrane. What is the work? Well, I did compute the displacements in the previous case, yes? So along this direction, the work would be S times U. And along this direction, it will be S times U. So you see that the work is twice 2 times S. Now, of course, this S here is what? Well, this S is a force per unit area in the reference configuration, because this is a nominal stress. But what is this area here? So you see this area that I am denoting here. So this would be L, this H. So in other words, I don't want to dirt the drawing, but you see the area of this face is L times H. So the force that is acting in this direction is SLH, okay? So this would be the total force acting in this direction. If this is the nominal stress, I have to multiply times the area, and then I have to multiply times the displacement. I have computed in the previous slide that the displacement is L times lambda minus 1. Okay, so that's it. What do we have to do at this point? Well, in fact, in this specific situation, I want you to remember that the first invariant will just be the trace of C. And if you notice how F is written, well, F is written, just let me do a miniature here, is lambda 0, 0, 0, lambda 0, 0, 0, lambda minus 2. Then if you do the square of this guy, then you see that the tensor C is equal to lambda squared, lambda minus 4. So this means that the first invariant of the formation, this is just 2 lambda 2 plus lambda minus 4. So in other words, if you want to rewrite it more nicely, this expression is only a function of lambda. So we get a u of lambda is in fact equal to, well, I want you to notice also that from these expressions, the quantity L squared H can in fact be collected from everywhere. So I can just write this is equal to L squared H, and inside of this bracket, I will now put this energy when it's evaluated in with this invariant. So instead of this I1, I put this guy. So this becomes, well, it would be mu divided by 2. Inside here, I put 2 lambda squared plus lambda minus 4 minus 3. Then I have to put the electric energy minus epsilon divided by 2 v squared divided by capital H squared times lambda to the power 4. And I simply have to write this guy, which I have to forget this piece here. So it becomes minus 2s times lambda minus 1. So what do I do with this energy? Well, what I do, I simply have to do exactly what I am used to do. I have to impose it is minimized. What is the variable? It's just lambda. So in this problem, you are prescribing a certain voltage, you're prescribing a certain loading at the external boundary, then you can compute the equilibrium lambda. And this is what I'm about to do in the next slide. So let me just copy this last expression. So I just want to paste here the expression I have obtained in the previous slide. Here we go. So I just adjust it a little bit. So this is my expression. Hold on, I just have to, I couldn't copy the whole piece all at once. What is missing here is the front stuff. So there was L squared H, and this is my total potential energy. And all this expression here, I've broken it, I'm sorry. So what I want to do of this expression is I want to find the lambda that minimizes the total potential energy. And you will see that it's very straightforward. So let me do this now. Well, what I have to do is simply to compute the partial, well, actually not the partial, but simply I have to differentiate u with respect to lambda. It's the only variable. So this is equal to, well, L squared H. So let me differentiate here. So I got here mu divided by 2. Inside here I got 4 lambda. Then here I got minus 4 lambda to the power minus 5. The minus 3 goes away. And here I get, well, I have to differentiate there. So this becomes 2 epsilon. And then I get v squared divided by h squared. And here I got lambda cube. The 4 and 2 have simplified. And finally, I get here minus 2s. And here we are. We finally have to impose these quantities equal to 0. So from this expression, I want something we can do. Let us compute, for example, the function v as a function of lambda and s, which means this will give us how v is changing, v is changing if you change lambda, but of course they change together. Well, if I set this quantity equal to 0, now first of all I want to simplify that expression. And just let me show you one thing. If I simplify here, you see these 2 actually get simplified with these and these. They become 2 and 2, but however, these 2's, they then get simplified with those there, okay? So essentially the expression that you see above there can be rewritten very quickly as mu that factors lambda minus 5. And here, since I want to compute the voltage, I just leave the S here, which is the load, and then this is equal to minus epsilon. So when I shift this guy on the other side, it becomes minus, and so this becomes epsilon v squared divided by h squared lambda cube. And from this expression we immediately get what we wanted, which is the voltage as a function of the stretch and of the applied load. This is equal to, well, just let me put, well, this would, in fact, this h can be put in front, so this becomes the square root of, well, on top I have mu lambda minus 5 minus s, and here below I have epsilon lambda cube. That's it. Isn't it beautiful? We have been able to understand how the stretch, the voltage, and the applied loading are related in the membrane. Now, before checking if these corresponds to what we observe in the experiments, I want to plot this function. So to plot this function, I've actually, for simplicity, I just put mu equal to 1 and epsilon equal to 1. And I've plotted this curve for various values of the value of the s, okay? So s is equal to 0, to 1, to 2, 3, and so on, okay? So this is what I observe. So that's it. In this slide, you see I have plotted again, once again, this is in the ordinate here, this is v. Let me use the blue, maybe there's a better contrast. So this would be the voltage. And here I'm saying the lambda. In other words, this in fact is telling you, and this first curve corresponds to no dead loads, no loading applied to the external. But then you see these other curves, they correspond to situations in which I'm applying weights, okay? So for example, this is equal to 1, and here I apply a weight which is S equal to 2, and then I apply a weight which is equal to 3. But what it is interesting, there are very interesting things. Let's stick to the situation that I've described. Let me put the video of the breaking membrane. So here we go. This is exactly the situation that it is described in this plot. This plot is telling you, when I apply the voltage, you can proceed on this curve. You see the lambda is increasing, up until, look what happens, you reach the peak of this point and you break the membrane. So I want to play it again because you see, well, in this case, actually, there are the loads. This would be the behavior in the absence of loading. But you see what happens? You reach a maximum value. And when you arrive at this maximum voltage, you cannot increase it anymore and you break the membrane. So you see, this also shows that this maximum point here, and this is true for all the various situations that I've described, this maximum point that you can see here takes a name of electromechanical instability. So this would be electromechanical instability. Now, I really do not pretend, or better, I do not claim that the material we've seen in this course is exhaustive for the set of problems that can be studied through nonlinear elasticity. There are many examples, many more examples that can be studied in a very clean way. For example, I didn't talk about the bending, and I didn't talk about the instabilities, which can still be tackled in a very nice and powerful way by coupling ideas coming from energy minimization with ideas of calculus of variations. To describe and cover all this material, it would require probably another course. But at least we have a window on the modeling of soft materials through this powerful subject that gives you essentially the same ideas of linear elasticity, equilibrium, constitutive equations, analysis of deformations, but in the three-dimensional context, you see everything becomes more interconnected, and this complexity is also behind the complexity of the behavior of soft material. I think I will just close it here, and vi dico semplicemente grazie per aver seguito questo corso e ovviamente rimango a vostra disposizione per tutti i chiarimenti laddove anche essi arrivassero e giungessero dopo che avrete visto queste lezioni, anche molto tempo dopo. Io sono sempre a vostra disposizione, conoscete il mio indirizzo email. Con questo io vi saluto e spero che questo viaggio vi sia piaciuto. Un caro saluto e grazie.